Today we're going to be in the Chapter 4 AP packet on page 6, and we're going to be learning how to balance a redox reaction in acidic solution and in basic solution. In an acidic solution, the steps are going to be element electrons, water, and H+, versus a basic solution is going to be element electron, water, H+, and then OH-. The first step that you're going to do is you're going to figure out the oxidation numbers of each element. So remember our rules. We know oxygen is -2. The sum of that is -8. Something plus -8 must be -1, so this must be a +7. Iron element by itself with a charge is going to be a +2. Here it's a +3, and here Mn is a +2. Now what we're going to do is we're going to realize what went up and what went down. So if we balance element electrons that way, we're going to see that the Mn went down from +7 to +2. That's a difference of 5 going down by 5, and this is a difference of 1 going up by 1. What we want to do is you want to make these two numbers match with the least common denominator, or least common multiple. So the least common multiple of that is going to be 5. So we want to multiply this by 5 and multiply this by 1. What this means is you want 5 irons on the left to change and go up in charge by 1, meaning losing electron, for every 1 manganese to go down by 5 and go from +7 to +2. So this is the sum of how many you want on each side, 5 irons. So you're going to need to put a 5 here and a 5 here. And then you want 1 manganese on that side and 1 manganese on that side. Remember, when you go up in charge, you're losing electrons. So when you lose electrons, you're oxidized. And that means there are 5 electrons lost total, 5 times 1 lost. And then you're gaining 5 electrons here times 1. So all the electrons lost in oxidation are all the electrons gained in reduction. All right, so now that we've handled that, we're going to take a look at water. Water is H2O. So we're going to use water simply to balance the oxygens. Water is only balancing the oxygens. So we see we have 4 oxygens on the left, no oxygens on the right. So we're going to need 4 oxygens. Therefore, I'm going to write 4 waters. Again, that was only for the O's. We didn't even care about H's yet. Now that we're done with the O's, we're going to go to the H's. So when we do that, we're going to realize that the right side of the equation has 8 hydrogens. This has no hydrogens at all. So I'm going to need to put 8 hydrogens on the left side. And now I'm completely done balancing the equation in an acidic solution. So we did element electron, oxygen with water, H with hydrogens. Next, we're going to move on to the basic. The basic solution is exactly the same with one extra step. So we're going to do the same thing again. We're going to write our oxidation numbers on top of here. So this was a -2, -8, +7, because that was the missing one. This is also a +2, this is also a +3, but now we're making manganese dioxide, which happens to be MnO2, so that's a -4 total. This has to be a +4 total. Again, we're going to look for what went up and what went down. So that's going to help us with our element electron balancing. So Mn went down again, but this time it went down by 3. And the Fe went up by 1. So I need the least common multiple, which is 3. So I want 1 of these for every 3 of these. So I'm going to put a 3 in front of the Fe's and a 1 in front of the Mn's. Now here's a little note in case you run into a problem. If this Fe had been diatomic for some reason, and there would be a little 2 down here, which I'm going to erase in a minute. If there were a 2 here, that would be a problem. What I'd have to do is I'd have to double everything, because there's no way you're going to have 3 Fe's with a subscript of 2. So you would double this 3 to a 6 and double this 1 to a 2. And when you do that, it would still work out to be matching up. Okay, so if there's a diatomic with an odd coefficient, it's going to require you to double everything. All right, now we're going to do the waters. Again, water is only to balance the oxygen. So if I have 4 O's on the left and I already have 2 O's on the right, I'm only going to want to put 2 waters over here. And that was to balance the oxygens. Now I'm going to focus on the hydrogens. If I look at my equation, I have 4 hydrogens on the right. I have 0 on the left. So I'm going to put 4 H pluses here. Now the extra step is the hydroxide step. The reason why I need this step is because this is a basic solution. If you have a basic solution, you cannot have H pluses floating around. That would make it acidic. So on paper, what you do is you neutralize your H pluses with OH minuses. So the exact same number of H pluses you have floating around by themselves, you have to add the exact same number of OH minuses as well. But you have to do that to both sides, because before I wrote down the OH minus, everything was already balanced. The left side and the right side were totally right. So if I add 4 OH minuses on the left, I have to also add 4 OH minuses on the right to keep things even. Now when you look at this, you'll notice that these 4 H pluses and 4 OH minuses, they actually form 4 waters. And the last step is to simplify. So if you simplify this, you're going to see that 4 waters and 2 waters, these are going to go away, and this is going to turn into a 2. So if you're going to rewrite this to be a little neater, you would write 2 waters plus MnO4 minus plus 3 Fe plus 2s will yield 3 Fe plus 3s plus MnO2 plus 4 hydroxides. And that again is the difference between balancing in an acidic and a basic solution.